and thank you for attending this webinar, jointly presented by Micromeritics Instrument Corporation and Rigaku on analytical methods to ensure battery raw material and electrode performance. My name is Jeff Kenvin, and I am the Vice President of Science at Micromeritics, and I will be the moderator for this webinar. Before we begin, we want to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you may use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off of your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. Founded in 1962, Micromeritics is a global leader in the manufacture of analytical instruments to characterize the textural properties of powders and porous materials. The earliest innovations from Micromeritics include the first commercially available gas adsorption analyzer for understanding the BET surface area and porosity of fine particles and porous solids. Building upon these innovations, Micromeritics now provides leading technologies for measuring the density of solids, catalyst and sensor characterization using selective chemisorption, advanced benchtop and custom reactor systems for evaluating catalyst performance, and market-leading instruments for powder rheology and powder flow characterization. For more than 7 decades, Micromeritics instruments have been used globally in the laboratories of the leading academic and industrial researchers and manufacturers. Micromeritics instruments provide accurate characterization and textural properties of materials from discovery through production. Since its inception in 1951, Rigaku has been a leader in analytical and industrial instrument technology. Today, with hundreds of significant innovations to its credit, the Tokyo-based headquarters Rigaku Group is a world leader in X-ray diffraction, thin film analysis, X-ray fluorescence spectrometry, small angle X-ray scattering, X-ray crystallography, computed tomography, thermal analysis, Raman spectroscopy, the manufacture of X-ray sources and optics, and semiconductor metrology. Rigaku products are used in research and analysis in a wide range of fields and materials. They are used in advanced and new materials research, battery research, chemistry, geology, minerals, material science, and much more. Pleased to introduce Dr. Katharina Peikert. I've had the pleasure of working with Katharina since she joined Micromeritics in 2016. Prior to joining Micromeritics, Katharina received her doctorate in chemistry at the University of Hamburg, and she has extensive experience with the synthesis and characterization of MOFs, zeolites, and porous materials. Dr. Peikert is currently a senior application scientist and the European application manager for Micromeritics. Also joining us today is Dr. Stephan Wollstadt. Stephan graduated from the Technical University of Darmstadt in the field of material science. His PhD thesis was focused on the development of fluorinated oxide materials for cathode application in solid oxide fuel cells and other electrochemical systems. Powder X-ray diffraction was a centerpiece of his thesis, and he was able to perform insightful structural analysis and thermodynamic calculations. Stephan joined Rigaku in early 2022 and is currently a member of the application team for Rigaku Europe Southeast as a specialist in the area of powder X-ray diffraction and Rietveld refinement. Stephan and Katharina, we are so glad you could be here today to share your insights on the characterization of battery materials.
Thank you, Jeff, for the introduction, and a warm welcome from my side also to everyone joining this webinar today. Looking at the entire battery manufacturing process, from quality assurance of the raw materials to production of precursor compounds, for example, coding, calendaring and testing of electrodes, as well as the finished battery cells, we see on this chart that Micromeritics and Rigaku offer analytical solutions that can help in kind of every single step of this process. Today in this webinar we want to focus on raw materials and the electrodes, and we will show you in some examples how our instruments benefit your process or product control. The first part about the raw materials, I will start by talking about density, powder flow and adsorption. Then I will hand over to Stephan from Rigaku, who will tell you more about elemental composition, phase analysis and crystal structure. The first instrument I want to introduce to you is the AccuPick. Our AccuPick is our gas picnometer, which uses gas displacement as method. We usually measure with inert gases like helium and nitrogen. The chambers inside the AccuPick are precisely calibrated, which makes it possible to measure the displaced volume from your sample. By this, the AccuPick can be used to calculate true, absolute, skeletal or apparent volume and density of your materials. This can be a really good technique for a really quick and simple quality control check of your raw materials. If, for example, you know that your material has an inherent material property of a density of 5.1 gram per cubic centimeters, you might set your internal tolerance, and by tracking the density over time, you easily see when one batch falls out of this range, for example by impurities. One specific example, the lithium iron phosphate, which is a common lithium source for lithium-ion batteries, might change the density just in order of different ion contents, and you easily can track this with just measuring density. Density measurements are usually a very quick experiment. I would say it takes between 10 and 15 minutes to get a value for your material. The GeoPick is another instrument of our density devices. It was originally designed for the determination of envelope volume and density. And combining these data with the AccuPick data that I just introduced to you, it's possible to calculate the percent porosity or the total pore volume of a porous sample. In addition, the GeoPick comes with a tab option, which makes it possible to measure bulk volume and density. And bulk density is a key parameter when it comes to storage as well as the processing of electrodes. At this point, I want to highlight how the GeoPick operates, especially in comparison to classical tab analyzers. As you can see in the picture, there is a glass chamber which is placed horizontally to the instrument. The sample is filled into this chamber, and a plunger is used to compress the sample with a certain consolidation force. This means the measurement takes place in a closed vessel, and on top it is even possible to place the GeoPick inside a glove box. The graph that we show here shows the bulk density of 3 different samples, and it shows how the bulk density changes with the different consolidation force. So with this technology, you not just get the bulk density of your material at one specific force, but you can even investigate how different forces applied to your sample have an influence on the bulk density. Our powder rheometer, the FT4, is a very versatile instrument that is designed to simulate a wide variety of process conditions. It can characterize your powders for their resistance to flow and motion, shear strength, the shear against the wall of the machine or apparatus you're working with, the bulk density as well, and compressibility and permeability of your powder bed. These powder flow properties are, for instance, key parameters when it comes to improving slurry homogeneities, electrode yields, or it helps you also to better control batch-to-batch variations. I decided to show you one example where we used the FT4 to analyze 3 different batches of lithium iron phosphate. With this material, we know that only minor physical variations can affect the performance and the yield. With this example, let us look at specific energy. Specific energy is a rheological property that can influence how a powder will mix and disperse. And it quantifies the degree of mechanical interlocking and friction between particles. In general, lower values are typically associated with more regular spherical particles. We tested 3 different batches from 3 different suppliers and looked at the specific energy that we got or measured for these 3 different batches. The graph shows you the comparison. As you see, batch 1, the blue batch, has the lowest specific energy, which indicates reduced mechanical interlocking and friction between the particles. This leads to the assumption that the particles are less likely to agglomerate and can disperse more uniformly. And we could also confirm this in the manufacturing experience, where batch 1 did produce a more homogeneous slurry, resulting in a higher yield electrode production. Batch 2 and batch 3 in comparison generated higher specific energies, and in manufacturing exhibited inconsistent performance, including blockage leading to system downtime or out of spec products. With this example, I just showed you one test of the many tests that the FT4 can do with your powders. If you want to learn more about how the FT4 can help you in battery production, we linked you a webinar as well as an application note specifically to this topic. The next topic takes us even further from quality control to R&D. How can I predict my raw material yields a good electrode performance? I think this is an important question, and especially as it can take months to find out which starting material resulted in the best battery performance or electrode performance. I think gas adsorption might help you to get some answers to this. Gas adsorption in general gives us information about a material's surface area, pore size distribution and pore volume. Before I come to a specific example here, let's take a closer look to porosity in general. When we talk about porosity, we are most likely also talking about pore sizes. This slide shows you the different definitions defined by UPAC for pore sizes. Pore sizes that have a smaller diameter than 2 nanometers are referred to as micropores, separated into ultramicropores and supermicropores. In the range between 2 and 50 nanometers, we find the mesoporous range, and pore sizes with a diameter larger than 50 nanometers are referred to as macropores. I highlighted you in blue the range that can be covered by gas adsorption, which goes approximately up to 300 nanometers in diameter. If you have pore sizes that are larger than this range, the mercury pore symmetry is the method of choice, and I will give more examples about this later in this talk. So looking at gas adsorption, what parameters can we get? We get information about the so-called BET surface area. We can calculate micropore and mesopore pore size distributions in the range, as I mentioned, between 0.35 nanometers and roughly 300 nanometers. Also, pore volumes can be calculated. Mercury intrusion gives us also pore size distributions, but this time in the mesoporous and macroporous range, and the limits here are between 3.6 nanometers at the lower end and around 600 micrometers at the higher end. Looking at gas adsorption, the measurement itself and the principle is relatively simple. The pressure of an adsorptive, which is usually nitrogen, is successively increased above the sample. At first, adsorption will occur only at single sites, where the interaction between the surface of your material and the adsorptive is the strongest. At increasing pressure, we will then build a monolayer of adsorptive, and with even further increasing pressure, a multilayer followed by the pore filling will occur. When we measure gas adsorption, what we get is an isotherm, which is the adsorbed volume plotted versus pressure. In general, we refer to this adsorbed volume to the relative pressure. This hypothetical isotherm shows you the different ranges of the isotherm that are used for different calculations. You see, for instance, that the micropore filling occurs at the very beginning at very low pressures. For BET calculations, we refer to the red marked range, which is the multilayer adsorption range, which typically is between 0.05 and 0.3 as relative pressure. At higher pressures, mesopores fill, and we can use the end of the isotherm to also calculate the pore volume for the whole range of pores that could be filled with the gas adsorption experiment. The example I brought you for using gas adsorption in terms of battery manufacturing is the comparison of 3 different carbon precursors. We tested graphene oxide, graphene, and graphite. You see in the graph that we tested all 3 of them with 3 different of our instruments. And first of all, we see a very good agreement for the values we got from the different devices. Furthermore, we see that the different precursors have surface areas in quite different ranges, which is around 250-260 square meters per gram for the graphene oxide, around 17 square meters per gram for the graphene, and much lower with only roughly 3 square meters per gram for the graphite. The surface area and the porosity in general has an influence on the behavior of the electrode, and by knowing those values for the precursors, as especially surface area is linked to particle size, pore size and porosity, this might help you to predict the behavior of your finished electrodes. Physisorption experiments can also be used to calculate DFT surface energy. The DFT surface energy method characterizes the surface energy heterogeneity, which reveals you the level of interactions between the adsorptive and the surface of your sample. The surface energy distribution, like we see in this graph, is obtained by plotting the incremental surface area against the adsorptive potential energy in Kelvin, which relates to the isosteric heat of adsorption. The colder the temperature, we can say in general, the lower the interactions between the surface and the adsorptive gas. And a warmer temperature means there are stronger interactions. Adsorption energy reveals the surface topology of graphite or graphenes. And the adsorption potentials ranging from 50 to 60, like we see in the graph, represent the basal planes. You see in the graph on the left side the different planes and phases that we can have in graphite materials. Values below 50 Kelvin represent prismatic surfaces, and those above 60 Kelvin then occur in terms of defects that you might have on your carbon surface. Adsorption potentials that are less than 20 Kelvin represent nitrogen condensation, so this is not that much related or not related at all to surface energy of your material. You also see a little peak or a starting peak around 100 Kelvin. This is the range where the energy refers to the presence of micropores. We see from the graph that the 3 different materials, the same that we discussed on the previous slide, have quite different behaviors in terms of their surface energies. The graphene oxide consists of prismatic phases, basal planes, as well as defects, where the basal plane contributes the most to the total surface area. It also shows some presence of micropores. In comparison, the graphene has stronger interactions with nitrogen in comparison to the graphite sample, and in total we see that the graphene oxide exhibits the strongest interactions with the most surface area. This tool can help you to reflect the degree of graphitization of your materials, and in contrast to other methods that you might know for surface energy determinations, the big advantage of this technology is that as we use a powder sample, it consists the entire surface. So it represents the material and not just a little picture or a zoomed in picture of your material. By this, I hand over to Stephan.
Thank you very much, Katharina, for those interesting insights into the portfolio of Micromeritics. From now on, we will talk about some Rigaku devices, which are interesting when it comes to the analysis of the elemental composition, when it's about the phase analysis, and of course when you're interested in the analysis of the crystal structure. First off, we will have some brief introduction into the interaction of X-rays when they come in contact with matter. Whenever X-rays hit on matter, we can observe various effects such as scattering, fluorescence, transmission and absorption, but also other side effects such as electrons or heat. Scattered X-rays carry information about the crystal structure, since the scattering angle depends on the lattice spacing connected via Bragg's law. On the other side, the X-ray fluorescence is triggered upon the de-excitation of atoms which were excited by incoming radiation. The emitted X-rays carry specific information about the fluorescing element. Transmission and absorption is something we may need later for the computer tomography, for the CT application, so more about that later. So the question is, what kind of information can we draw from X-ray diffraction and or X-ray fluorescence? How do they differ? So XRD is used for analyzing crystal structures and quantifying phase mixtures down to several few weight percentage. Now, on the other side, the crystal structure is an individual feature of each compound and can be seen as a fingerprint we record with the XRD. See, for example, on this slide, rutile and anatas. They have the same chemical composition, but they differ in terms of crystal structure. On the other hand, XRF delivers elemental information of the investigated material and can be used to quantify elements down to a few ppm. Compare here, for rutile and anatas, we get the same signal in the XRF. Though the techniques are complementary and work well together, we cannot directly compare them to each other. XRF for battery application can be used to, for example, investigate the composition or the cation content in for example, a laterite ore, which contains nickel, which is very interesting for the battery application. For XRF, it is important to have well-prepared samples. This can either be achieved by so-called fusion sample preparation, but also by simple powder pressing. Of course, fusion preparation delivers much more precise measurements. They have very, very high precision. On the other side, pressed powders, of course, are faster and easier to achieve, but they also deliver accurate results. Here you can see, for example, the analysis of laterite ore with the help of, for example, a Super Mini 200 or Primus 4. When it comes to XRF, it is important to ask, do I need a wavelength dispersive X-ray fluorescence device or an energy dispersive X-ray fluorescence device? The WDX enables the analysis of impurities, for example, aluminum and silicon, due to no overlapping of the peaks, as you can see down in the graphs. In contrast, EDX is faster, but it would deliver not so accurate values for this analysis. However, for both cases, we can also detect light elements such as fluorine. On the other side, we can also use XRF in a standardless fundamental parameter approach, which delivers, for example, in a nickel-cobalt mixture, the main compounds, but also compounds which are interesting in terms of ROHS. For example, here in this case, we can see the detection of lead. Some ppm can be detected, also done by the Super Mini or Primus 4. For those applications, we also have various application notes attached to this webinar, so I kindly refer you if you're interested to those application notes. When we now go from the XRF to the XRD, of course we change the physics a little bit, but with the XRD we can analyze our starting materials even further. For example, in this case, in this special case, the graphitization, where we analyze our graphite starting material, because the degree of graphitization is important when it comes to the battery capacity, so we can directly conclude from the results here to the later performance of the battery cell. In this special case, we have 3 different samples, A, B, and C, which differ in their crystal structure, but also, of course, in the degree of graphitization. Easy and fast measurements, and also the evaluation of these results is very simple and fast. If we now go further and think about the production of cell components, for example, NMC as a cathode material, we are probably interested in phase purity, whether or not the synthesis worked. And here, for example, we can use the Miniflex XPC or the Miniflex 600, our benchtop workhorse, and do quick and reliable scans of our cathode powder. And we can easily detect impurities down to only a few weight percentages. For example, here we have 1.57 weight percent of lithium carbonate in our synthesized NMC cathode material. On the other side, when we are interested in the solid state reaction of our raw materials, for example here, again in the case of NMC, we can perform so-called in situ XRD experiments for the solid state reaction, where we can directly observe the transition from raw materials, from precursor materials to NMC, in this case around 1000 degrees C. For that, of course, we would require a bit more sophisticated equipment. For example, in this case, our SmartLab SE, a floor standing device, because we would need to attach more sophisticated sample attachments on our diffractometer, which we are not able to do on our benchtop devices. On the other side, when we have air-sensitive materials, which we have to store or prepare in the glove box, of course, Rigaku also offers airtight sample holders, which are stored and filled in the glove box and then transferred due to their small sizes in small pass boxes to the XRD equipment, where they are then measured. As such, in this case, lithium phosphorus sulfur compound, which we left in the airtight sample holder over 3 days, and as you can see, the profile doesn't change. So over a long time range, the material stays stable inside these airtight sample holders, offers a great opportunity to analyze and investigate air-sensitive materials, which can also be done, for example, in the Miniflex 600, but also in bigger systems like the SmartLab systems. When it comes to the deeper understanding of the crystal structure, with the use of powder XRD, we can choose between two similar methods. One is the read-fed refinement and the other one is the pair distribution function analysis. Both rely on the powder pattern of our material, but the PDF analysis utilizes the whole powder pattern range. So it requires a larger queue space compared to the read-fed refinement, which only relies on the Bragg information, the reflexes. However, from read-fed refinement, we can draw information about the average structure, about the long-range order of our atoms, about the crystal structure. So, for example, lattice parameters, but also about the atomic coordinates and also the occupancy level of our cations, for example. On the other side, the PDF analysis offers us information about the local structure of the atoms. So in this case, for example, for lithium iron phosphate, we can precisely estimate, of course, the space group, the lattice parameters, but also the atomic coordinates, which will give us information, of course, about the overall structure, but also probably about the later performance. And for that, one would like to have a very powerful device, for example, the SmartLab 9 kilowatt with our rotating anode, which delivers a high flux and high brilliance. So we are able to record very nice and well-resolved diffractograms over a short period of time. On the other side, we can also use this information to calculate the bond-valence sums, which are important when it comes to the storage capability of lithium ions within our battery material. And with the help of our software, we are able to calculate the bond-valence sums, but also depict them, as you can see to the right. This special case for lithium iron phosphate, we see that, for example, lithium was found to be univalent, and on the other side, iron was found to be divalent. However, when you come across some secrets of your diffractogram, for example, as in this case, we see in the read-fed refinement, we use a cubic unit cell or cubic structure for the lithium manganese oxide, and we see that the quality measure of the read-fed analysis is not satisfying. We see with the help of the PDF analysis that this structure is actually of orthorhombic nature. So we achieve also with the help of the PDF a much better result. For this analysis, however, one would need a very high-performing device such as the SmartLab 9K system in order to record high intensity and well-resolved defectograms in a reasonable amount of time. So the PDF analysis offers much more insight into the short-range order of our materials. However, on the other side, it also offers more information compared to the read felt. So now at this point, I would like to hand over to Katharina again. She will start with the description of electrodes, and she will tell you more about the absorption analysis, the mercury intrusion porosimetry technique, and later on she will hand back to me and I will talk about the operando measurements of battery materials inside diffractometers, and of course we will talk about the computer tomography, the CT, the part imaging with the help of X-rays.
Thank you, Stephan. I will start by continuing with adsorption. Looking at this example, we see that this is an anode material, and for this anode material we measured the whole isotherm, including the adsorption and desorption branch. From the isotherm data we can now calculate the BET surface area and the pore size distribution, and already the shape of the isotherm tells us this electrode contains mesopores, what we see from the typical shape with the hysteresis closing at a relative pressure of 0.4. When performing physisorption experiments, we have to think about sample preparation, especially when working with electrodes or generally with foils. From the pictures on the left side, you see that different ways are thinkable. We already tested in our labs, on the one hand side, rolling up electrodes, like you see on the left picture, but we also performed tests where we just simply cut the electrode in smaller pieces. From our experience, both ways work, but a lot of customers prefer rolling up the electrodes because it doesn't destroy or doesn't have the risk of destroying the surface of the active material. For this example, I want to focus on BET. So why is BET important, the surface area, important for the electrode, the final electrode? Increasing the surface area of the electrode, for instance, could result in improved efficiency of the electrochemical reactions and can therefore facilitate the ion exchange between the electrode and the electrolyte, especially within an anode, as higher surface area permits shorter diffusion path to the lithium ions between the graphite particles. On the other hand, lower surface area materials might be better suited for improved cycling performance, resulting in longer battery lifetimes. The graph that I show here is an example of how BET surface area can be used for process control. To check, for example, how uniformly the coating and calandering process of the electrode went, different pieces from the different positions of the same batch were tested, and we see that they result in quite different surface areas, ranging from around 7 square meters per gram up to over 8 square meters per gram. So this is an easy measurement for process control at this part. Let's now look at mercury porosimetry. As I already mentioned, this is also a technique where we can calculate pore size distributions, pore volume, and even also surface areas. And like gas adsorption, mercury intrusion takes advantage of the relationship between pressure and pore size. But in this case, we work with much higher pressures, up to 400 megapascal. And the higher the pressure, the smaller the size of pore into which mercury can be intruded. Because mercury is a non-wetting liquid, the contact angle to the surface is larger than 90 degrees, and it does not intrude into the pores voluntarily. By measuring the change in capacitance, this method determines the volume of intruded mercury and can then relate it to the pore sizes. This method is in general very well suited to characterize the porosity and also of finished electrodes, especially if they include macropores that cannot be detected by gas adsorption. On this slide, I brought you one example where two different electrodes, which should have a similar performance, were tested and compared to each other. The graph that we see here is the pore size distribution. We see the intruded volume as log differential intrusion versus the pore size. For this material, we see that there are some larger pores in the range of 200 micrometers, and in this range, both materials behave quite similar to each other. Then we see a main peak for both materials. For electrode A, it's with the maximum at 0.9 micrometers, whereas electrode B shows the maximum at only 0.7 micrometers. So the materials are comparable, similar to each other, but still show some differences. And we also see from the higher peak for electrode 1 that this comes with a higher volume at this pore size. As I already mentioned, pore size distribution as well as pore volume and also percent porosity are the parameters that we can get from mercury intrusion measurements. I show you two pictures on this slide also from the preparation of this sample. The electrode was cut into or punched into circles, and those circles were put into the penetrometer, which is the kind of sample tube for this measurement. And you see, in order to fit the decent amount that we need for the measurement into this bulb of this penetrometer, the circles at many times lay quite close to each other. So the question might arise, is there also filling between just the different copper sheets or electrode sheets that could be shown as pore sizes in the overall result? And for this, in order to further investigate this, we also measured the pure copper foil circles, the same amount of copper foil circles as we used with electrodes. We see here now the intrusion curves of the different samples. In blue and red, again, the electrodes, and in green, the copper foil. And it's quite interesting to see that up to around 1 micrometer, maybe a little bit larger than 1 micrometer, the behavior of the intrusion curves is quite similar. This let us assume that this first part, this whole range, is simply due to the filling in between the different electrode pieces and doesn't show the real porosity of the material. So I assume that these two electrodes don't have pore sizes any larger than 1.4, 1.5 micrometers. With our software, it is even possible now to subtract this measurement of the pure copper foil. We can subtract it as a Planck run. And the result you see on the right-hand graph. We still have some filling going on, going up a little bit and down again. And I think that this is most likely due to just not being able to completely reproduce the loading of the sample into the penetrometer. You might have some larger spaces in one sample or in one penetrometer and some smaller spaces in another one, but more or less we can tell that here there is no significant intrusion going on. So for the overall characterization from this, we can say the pore filling and the porosity of these two electrode stars in this range around 1.5 micrometers. Another way of accounting for this filling processes is to simply roll up the electrodes. And you see on this slide how we did that with another electrode sample. We used a stainless steel spiral that you see quite nicely here, and we just put the electrode in between this spiral. We still have some spaces, and especially the space between the spiral and the electrode. So there might be some larger spaces also that will be filled with mercury only at a special pressure. But from the result on the left hand, you see that we can distinguish really clearly between the filling and the real pores. In blue we see here the intrusion curve, and in green we see the pore size distribution. So I think a value of around 740 micrometers is reasonable for the filling just in between the electrode and the spiral, and then the real pores that we can expect for this material have their maximum at 1.3 micrometers. With these examples, I now hand back over to Stephan.
Okay, thank you very much, Katharina. And once again, thank you very much for those interesting insights into your devices. In the following, I will show you examples for operando measurements with our XRD devices, but also part imaging with our CT devices. When it comes to the assembly or the preparation of full stack batteries, it might be interesting for the user, also for the scientist, how the performance of the battery looks like, what degradation mechanisms may be there, how structural changes look like. And for that purpose, Rigaku offers two different geometries. One is the reflection geometry and the other one is the transmission geometry. Both are simple sample stages which are mounted into our floor standing devices, for example to the SmartLab 9K system. Here it is to say that the reflection geometry is designed for liquid, but also for all solid state batteries, while the transmission geometry is specially prepared for pouch cells. Together with the sample stage, it is also necessary, of course, to provide a potentiostat, so a device which guarantees the charging and the discharging of the cell and monitors the voltage and current curves. Once this is set, also with the choosing of the proper source, for that case, Rigaku offers, besides the common copper source, also molybdenum source, which is much more suitable for analyzing thick cells and also these reflection geometry cells because of the shorter wavelength. Once this is set, the charge-discharging experiment can start. For example, in this case, a pouch cell attachment in transmission geometry, we see a nice experiment of charging-discharging the pouch cell. To the left, we see the defectogram of the corresponding phases. In the middle, we have two waterfall plots of interesting reflexes. The left one, the cathode, the NMC reflex, and to the right, the anode reflex of carbon. And the most right graph shows the charging-discharging cycle. What is clearly visible is the shift in the reflex of the cathode material and also the phase change in the anode material. You can see a jump in the carbon due to the phase transformation. From this, we can draw direct conclusions into the battery performance, but it would also be possible to detect other phases which form during the failure of a battery with the help of these attachments. And once again, for this one, you would require a floor standing device, for example, SmartLab SE, but of course also our SmartLab 9K system. And last but not least, we will have a look at the imaging of battery cells with the computer tomography, with X-ray computer tomography. It is possible to image different materials within the batteries. We can have a look at the heterogeneity, impurities and defects inside the battery structure, which may affect the performance, stability and durability of our battery cell. For that, we simply use X-rays, and we use the absorption and the transmission of our X-ray radiation. For example, in this case, the anode and cathode material are clearly visible. On the other side, voids and holes inside the battery are visible as black holes. And for this purpose, you would need a CT lab HX or a Nano 3DX. With the help of the CT, you are able to clearly identify the different structural layers of the battery. And this one is, of course, a non-destructive way to analyze established battery cell. And with this last topic, I would like to conclude this webinar. What have we seen? The first part about the raw materials. we saw how pygnometry was used for the quality control and also to describe material properties. We also saw how we could predict process performance by powder rheology, but also how we could predict electrode performance by the gas absorption. We also saw how the elemental purity of our precursor material could be estimated or analyzed by XRF. Further, we saw the phase identification and quantification, powder XRD and Rietveld analysis, but also we saw detailed structural information by XRD with the help of Rietveld and PDF. The last part dealt with the process control with the help of gas absorption. We also saw how to measure electrode properties with the help of mercury porosimetry, but also we were able to show the performance of batteries with the help of inoperando analysis in XRD, but also we were able to show what instrument to use for the imaging of manufactured cells to use for the error diagnostics, in this case our CT devices from Rigaku. And with that, I want to thank you for your attention, and please feel free if you have any questions to ask.